Okay, thank you very much, Arvid. Okay, so we are speaking about the ribosome flow model modeling, which is a good introduction to the network of RFMs that we will speak about tomorrow. Maybe we'll start today, we'll see, because this will also be a closed system where the total density of ribosomes is conserved. Before that, I just wanted to go back for a moment to the RFM, sorry, but I want to go back to the RFM and remind you that we proved that this quantity exists. This was the sensitivity of the steady state production rate when we make a small change in one of the lambda i's. And we actually got a formula, an explicit formula for this in terms of sigma, V, and all kinds of things. And so I forgot to say something important, at least in the context of people who know TASEP like you, that this means that there are no phase transitions in RFM, okay? No phase transitions. Why? Because this means the fact that R is differentiable with respect to lambda I means that if I make a small change in lambda I will always get small enough change in lambda I will always get a small enough change in R. There is no possibility that I will make a small change in lambda I and suddenly there will be a huge increase in R like we have in phase transitions. So in this respect, the RFM is different from TASEP, at least the finite dimensional RFM. It is possible, I think, that in the infinite dimensional RFM, we will have phase transitions. I'm not sure, but certainly in the n-dimensional one, this formula says that one, we can compute the sensitivities explicitly in terms of sigma and V, but it also says that we cannot expect any phase transitions. So, you know that this may be of interest to physicists, so I wanted to emphasize this. I forgot to say this, but I say it now. Okay, so now we go back to the RFMR, ribosome flow model on a ring. And we have these equations. I plotted here the case. I wrote the equations for the case of 3 sites, but of course, the equations look very similar for n sites, and all the results I'm going to speak about also hold for n-dimensional RFMR. And we said that an important property here is that the total density of particles remains constant along the solution. This is a first integral or an invariant of the motion. It has many names, and this is very important. It turns out that we can prove using the theory of cooperative systems. We showed that this is also cooperative. A cooperative systems with the first integral, that for any S level set of the first integral, so we take all the initial conditions, for example, where the total density is 1/2, This is what I call N1/2. N1/2 are all the initial conditions of all the states where the total density is 1/2. And for any such set, there is a unique equilibrium that depends on this S. And for any initial condition in this LS, the solution will converge to ES. So basically, every time we have to consider some fixed density, which can change. The fixed density can change from 0 to n. This is when all the sites start completely empty. So this is 0, and then this is when all the sites, we start with them completely full. And fix this density, because the dynamics makes sure that this density is constant. And for all initial conditions that give me this density, we will converge to this unique equilibrium point, ES. And of course, this means that for many initial conditions, we will converge to an equilibrium point, because any initial condition belongs to some LS or some S. Now, this raises an interesting question, of course, and the question is, if, and then this will be the steady state flow. It will be the steady state flow. The flow from any two sides looks like this: lambda I xi 1 minus xi plus 1. So lambda n minus 1, en minus 1 1 minus En. This is at the steady state. Again, we are always on some level set Ls. And now, there is an interesting question. Let's say that I change S from 0 to N. So here I look at the initial conditions with no ribosomes. Here I look at the initial conditions when everything is full, and I go through all the possibilities in the middle. What will RS look like? So when there are no ribosomes, of course, the equilibrium point will be that everything is 0. If everything here starts with 0, imagine that everything starts with 0, then everything remains 0. And then everything remains 0, we will have here 0, and Rs, when S is 0, which is R0, is 0. Now, if we start with everything completely full, this is S equal to N, means that the total density is N, but the total density is N only if all the sites are completely full. Then what will happen? If all the sites are completely full, so here you have 1, and this is 0, this is 0, this is 0, all the derivatives are 0, which means that when everything is full, this is an equilibrium point. So I will stay with everything equal to 1. The equilibrium point here, everything is 1, and in particular, because of this, I will get 0. And of course, there is no flow, because when all the sites are completely full, nothing can move. It's like Tassel with all the particles full, and remember, we are speaking now about the circular Tassel. So nothing can move. And it turns out that in the middle, you always have, and we can put this, you always have a shape like this. There is a unique S star, a unique density, so that if you start at this density, for many initial conditions on this level set, MS star, you will converge to an equilibrium, this equilibrium with S star, and there you have a maximal flow. And for many other initial condition, which is not on MS star, you will have a smaller, you will converge to an equilibrium and you will converge to a steady state flow, but it will be smaller. So there is one optimal value where the sites are not too empty and not too full. And when you start exactly at this situation, so you take an initial condition A. So we are speaking now about something called the optimal steady state flow. And this is a proposition 15 in the pages I've sent you. And it says that you fix the rate, lambda 1 up to lambda n, all positive, in your RFMR. And there exists a unique S star that is a function of these rates. It will depend on these rates. And so that this graph holds, so that you will see this graph. So let me draw it again. What is important is that here you have a unique equilibrium for Rs, for the flow. Rs star is the optimal steady state flow. And if we let E star denote the equilibrium at S star, just for simplified notation. So when I start from any initial condition with total density S star, I converge to the same equilibrium point, which we denoted by E star, but let's call it now just E star for simplicity. Then I can say something about the structure of this E star. It satisfies the following equality. When I multiply all the E stars and I multiply all the 1 minus E stars, I get an equality. And we can prove this from differentiating. We differentiate this by S and look for the maximum value and do some manipulations, this is the result that we get. So let me try to understand, to explain what this means. Let me try to explain what this means. If S is very small, then every EIS is small, because you know that the total density, when we sum up, after we reach the steady state, if we sum up on all the densities, this is just equal to S. S is this initial density that is conserved. This is the initial density that is conserved. And from any initial condition with this initial density, I will converge to this ES. But because the initial density is conserved, the density when I'm at ES, which is what is written here, is just equal to S. So if S is very small, so small I mean close to 0, imagine that this is close to 0, and this is a sum of non-negative numbers, so each one must be small. Yes, if S is, just as an example, 1 over 100, just as an example, then of course each one of these, each one of EIS must be 1 over 100 or less, because the sum is 1 over 100. So every EIS is small, and then because of this, I will get a small RS. And this will give me a relatively small RS, because RS includes here a multiplication by one of these EIs. If S is large, then the opposite case happens, then the opposite case occurs, some kind of symmetric case, but opposite. And because I have here 1 minus E, I will get also a small RS. So the idea is that when there are many particles, of course, the flow is relatively slow because we have traffic jams. Somewhere in the middle, there is a critical value S star, so that for this S star, you get the best possible production rate after you converge to the steady state. And for any other initial density S, you will get something which is smaller than RS star. We can also denote RS star for simplicity by R star. So R star and E star are the values when we are at this optimal initial density. Now, it turns out, maybe this is not surprising, that there is a spectral representation for the optimal situation, not for any situation in the RFMR, but we have a spectral representation for the optimal steady state case. So this is the case where we start from an initial condition x0 in LS star. So we look at we try to see what happens when we are really in this total density. So what this means is that the total density is equal to S star initially, and then it will be equal to S star all the time. This is just like saying this. And then the optimal density, then, okay, so fix some initial condition here, and let E star denote the equilibrium, and R star denote the this R ester, the steady state production rate or flow. So we look now for the optimal case. And the theorem, is it the theorem? Yes, theorem 16 in the notes says the following: generate a matrix B, which looks like this. You put zeros on the main diagonal. We define now a matrix B. In the RFM, we had a matrix A that gave us a spectral representation of the steady state. Now we have a matrix B, and what is the difference? If we put lambda 1 up to lambda n minus 1 to the power minus half, this is now a matrix n by n. In the RFM, it was a matrix of dimension n plus 2 by n plus 2. Now it is n by n. Here they are all zeros, except that now I have a new entry here, lambda n minus half. Because in the Jacobian I also had a new entry corresponding to the cyclic situation in my matrix. And all the rest are zeros, and here you fill out symmetrically. So the matrix is symmetric. You just fill it up so that the entire matrix will be symmetric. Then okay, let sigma sig V be the Perron root and eigenvector of B. So again, this is a matrix which is component-wise non-negative, and it is also irreducible. We will speak about this soon when we speak about strongly monotone systems. So it is a component-wise non-negative and irreducible. This means that we can apply the Perron-Trompenian theorem, and there exists a dominant eigenvalue sigma, which is simple and positive, and the corresponding eigenvector V is all entries positive. Then, so all this was the if part. Then R star, the optimal flow at the steady state, but corresponding to S star, everything now we are on this S star, the best density that we can start with, and also EI star is VI plus 1, sigma I 1 half, sigma VI. So very similar to the spectral representation in the RFM, but here it doesn't work for any steady state, only for the optimal steady state. There is some S star, there is some density, so that for this density, when I look at the steady state flow, I get a maximum. This is when the RFM in some sense is not too full and not too empty. The RFM is not too full and not too empty. I consider now only this case. For this case, I can get R star and EI star from the spectral properties of the matrix. And the proof of this is not so complicated. Again, you just write the equation BV is equal to sigma V. This is the equation that says that sigma is an eigenvalue, V is an eigenvector. And you start manipulating the equations, and you will get to a set of equations which is exactly the equations of the steady state of the RFMR, including this equation. This equation characterizes E star, which is what we are interested in. So you follow more or less the same procedure as you do in the RFM, and you get this result. And now an interesting observation, I think it's interesting. Consider B and take lambda n to infinity. We take this matrix and we take one of the rates. This is the rate from site n to site 1. We take it to an infinite value. And then we see that this goes to 0. This also appears here, because this matrix is symmetric. This also appears here, but this will go to 0. Because they go to 0, B actually goes to the matrix A in the RFM-R, the matrix that gave us the spectral representation in the RFM-R, but this matrix will be of dimension n plus n, n by n, because B was n by n. In the RFM, when we had an RFM with n sides, the spectral representation considered was based on a matrix like this. And it had this structure with zeros here. And this is exactly the structure we get now. But now we get A, which is Rn by n. So actually this corresponds to an RFM with n minus 2 sides. If I write here. This was an RFM with n sides. And the spectral representation included a matrix A that was n plus 2 by n plus 2. Now, because we started from B, which is n by n, and we took lambda n to infinity, we get exactly the matrix in the spectral representation of the RFM, but of dimension n by n. So this corresponds to an RFM with n minus 2 sides. And I want to explain this intuitively. Why is this so? So imagine that you start from the RFM-R with the optimal density, the optimal initial density, n sides. And from the last side, because this is an RFM-R, you flow with the rate lambda n to the first side. Now I'm taking lambda n to infinity. Lambda n was the rate from the last side to the first side. When I take lambda n to infinity, what will happen? I claim that this will completely fill up because I have an infinite rate. This will completely fill up, and this will completely empty. This will be completely empty, again, because the rate of flow outside of this side is infinite, and the rate of flow into this side is infinite. And then what do I have left? I have left here a linear chain of sides, and this chain is fed by a reservoir that is completely full. This is completely full now because lambda n is infinite. So I'm left with a finite chain. This finite chain has n minus 2 sides. You see, it begins with side 2 and ends with side n minus 1. So it has n minus 2 sides. It is fed by a completely full reservoir, and it feeds a completely empty reservoir. So this is just the RFM. Okay? Once we know that we are left here with a linear chain which is fed from a completely full reservoir and feeds a completely empty reservoir, this is just an RFM with n minus 2 sides. And we know that for an RFM with n minus 2 sides, we have this matrix that gives us the spectral representation, and it is exactly this matrix that we started from here, B, in the RFM-R, when we take lambda n to infinity. So in some sense, so let me write this down because maybe it's important. If you take the RFM-R with in the optimal situation, when we start with an initial condition or initial density which is conserved in LS star, and then you take lambda n to infinity, then this gives you, this is with n sides, then this just gives you an RFM with n minus 2 sides because of this intuition here. Because when lambda n goes to infinity, this is a completely full reservoir feeding this linear chain, and this is a completely empty reservoir, and you're fed by the chain. So this is just an RFM with n minus 2 sides. And what this means basically is that if you know how to analyze the RFMR, the ribosome flow model on a ring, and for example, if you know how to develop a spectral representation for the RFMR using this matrix B, then automatically you know how to analyze an RFM, and you know the spectral matrix for this RFM. Just take lambda n to infinity in the RFMR. So I hope this is more or less clear. I'm not sure about tassel. If you take a circular tassel and you take one of the rates, say the rate from the n side to the first side to infinity, does this give you a linear tassel? I'm not 100% sure, because here again, it only happens for initial conditions in this S star. So you have to take a special situation. It's not for any RFMR, only for initial conditions in LS star. Okay, that was more or less what I wanted to say about the ribosome flow model on a ring. That's a good time to ask if you have any questions.
So Michael, I have a question. Here the rates are fixed, lambdas are fixed. So what if the rates are stochastic, or could we analyze from such kind of spectral theory that we have the matrix for RFMR to deduce some output rate for the system?
So for example, that's a good question. So for example, we can show that if the rates in the RFMR are now time varying and jointly T periodic, we can show using the theory of cooperative dynamical systems with the first integral. Actually, it would be capital T periodic cooperative systems with the first integral. We can show that every solution converges to a periodic pattern. In the RFM, we needed contraction theory to prove this. This system is not contractive. The RFMR is not contractive because the density remains constant. So in some sense, trajectories don't necessarily become closer to one another. But there is a result on cooperative, so T-periodic cooperative systems with the first integral that says that the system entrains. So when you put T-periodic inputs, and this will correspond here to T-periodic, jointly T-periodic rates, every solution will entrain, will converge to a T-periodic pattern. So this we can say. More general cases, I'm not sure. Using the spectral approach, you can get some results. For example, we didn't do that, but you can get some results. For example, the idea is the following. We did this for the RFM. Suppose now that the lambda i's are not constant, but they are stochastic variables. So every time, think of it as if every time you draw a new value for the lambda i's, you make a draw, and you get some values according to some stochastic rule, so some probability rule for your lambda i's. And then you get another choice for your lambda i's. Every time you sample them according to their probability. And for any time you sample like this, so let's mark these with bar to denote that they are different from these. Every time you sample them, you get a new steady state and a new production rate. And then you can ask, okay, what will be the average of all these production rates? Because you know the average maybe of the lambda i's. So you can ask questions about the stochastic properties of the system now. So for example, what is the average, or what is the what is the distribution of the steady-state production rate. And this becomes a problem in stochastic matrices, because you have now a matrix and you put here some stochastic variables, and you know that the round root is always this R up to power -2. So you can get some interesting, I think, stochastic results also in the case where you assume that all the lambda i's are stochastic. In this case, when all the lambda i's are stochastic, we think very relevant for biology, because of course the cell is a very stochastic environment. You don't know really the values, and maybe they change all the time. So assuming that there is some stochastic, that you don't know the exact values, but you know some distribution, perhaps makes more sense than assuming that the rates are just constant. Sorry for such a long answer, but yes, please, Aditya, I heard that you wanted to say something also.
Yeah, I get the point. Okay, we can study about stochasticity by comparing those matrices and the mean values, maybe with the component wise with the matrices, and see how as n tends to infinity, the steady state production rate tends where it tends.
Yes. So once we have this spectral representation, we can also consider the stochastic case using the theory of stochastic matrices, because now I have a stochastic matrix and I'm interested in the distribution of the round root in this set of stochastic matrices. And this is a classical problem, of course, in stochastic matrices. So we did this one paper on this for the RFM. This can also be done for the RFMR, but we didn't do that. Okay, so more questions about the RFMR. Thank you, Aditi. More questions about the RFMR before we continue? I will raise the board in the meantime, and if anybody has questions, please don't hesitate to ask. So we spoke about monotone dynamical systems. And now I want to speak about strongly monotone dynamical systems. And I will make a table here so that it will be easy to understand the difference between these two. And this is important because actually many of the results from the theory of monotone dynamical systems or cooperative dynamical systems hold for this case. We need the strongly monotone systems. Jiang theory was enough to be here. Jiang theorem worked here. But other results, like the fact that for a monotone system with a first integral, everything converges, every solution converges to an equilibrium, we actually need the stronger assumption or the stronger condition that the system is strongly cooperative or strongly monotone. So I want to explain what this is. I want to show that the RFM and also the RFMR, but it's enough for now on the RFM. I want to show that the RFM is a strongly monotone system. And then when we move to networks, these will also be strongly monotone dynamical systems. So we have a dynamical system. First of all, we take two vectors and we say that P is smaller or equal to Q if this holds for every coordinate. I'm just reminding you what we did with monotone dynamical system, and then the system is called monotone. So I have a system which can be linear, non-linear in general, but of course can also be linear. And then we said that the system, so this, and then the system is called monotone if whenever you take two initial conditions which are ordered, the solutions respect or preserve the ordering for every time t. The solutions along your nonlinear dynamical system or dynamical system preserve this. And for linear systems, this happens if and only if A is Metzler. Okay, so let me write it down. Here, x dot equals ax is monotone if and only if A is Metzler. And x dot equals fx is monotone. Now it's not necessarily an if and only if jx is Metzler for any x in the state space. But that's enough. We don't need an if and only if condition. We just need a condition that it's easy to check. And it's easy to check the signs of jx and to see if it's Metzler or not. Now I want to introduce first of all a stronger ordering. P is smaller, P is like this is a notation, if and only if Pi is smaller than Qi for every I, strictly smaller. Here we allow smaller or equal. Here we require that every entry in P will be strictly smaller than any entry in Q. And definition, the system x dot equals fx is called strongly monotone if whenever you take two initial conditions which are P smaller or equal to Q and they are not equal, okay, if they are not equal, it's not interesting, it's the same initial condition. So take two initial conditions which are not equal, then xtp is strictly smaller than xtq for every time positive. So what does this mean? You take two initial conditions which are ordered, because you have here p smaller or equal to q and p different from q. So the typical situation would be something like this. This is 1, 2, 3, and this is 1, 2.1, 3. At least one coordinate. The two vectors should be smaller or equal to 1, and they should not be equal. So this means that there is at least one coordinate where you have a strict inequality, but not necessarily in every coordinate, only in one of them. And this says that here you will have strict inequality in every coordinate. So in some sense, the system takes this smaller or equal and makes it even stronger. It makes it strictly, this, remember, this is the definition. This means that xitp for any entry a, I, is strictly smaller than this for every I and for every t positive. Strictly smaller. So in some sense, so you understand why it's called strongly monotone, not just monotone, because now we require something more. And somehow the solutions must take into account all the entries, and they should see that in one of the entries it's not only equal but strictly smaller, and then this should propagate to a strong inequality in all the entries now, because this is what this notation means, that you have a strong inequality in every coordinate or in every entry of the vector. So now what we want to do is we want to find conditions, sufficient conditions, guaranteeing that our system is indeed strongly monotone and not just monotone. And I will actually give this condition and maybe also prove it, because it gives some intuition, I think, and also it leads to an important notion for linear algebra, which is the notion of reducible and irreducible matrices. Some of you maybe know it, I don't know, I will review this notion of reducible and irreducible matrices and also try to give it some intuition. And this will play an important role here. So the condition for strongly monotone, for example, in linear systems, the condition for strongly monotone is, of course, that A is Metzler. This is, of course, necessary because if A is not Metzler, it is not monotone at all. So certainly it is not strongly monotone, plus A is an irreducible matrix. An irreducible matrix. Sorry that my handwriting here is not so good, but it's written here, A is an irreducible matrix. And these two conditions together will give us strong monotonicity. Here, in the nonlinear case, we need the Jacobian to be Metzler and irreducible for almost every point X in the state space. This is the condition for strong monotonicity, and then we can use a lot of results on the asymptotic behavior of strongly monotone systems. So let me talk a little bit about reducible and irreducible matrices, because as I said, this will play an important role in the analysis of strongly monotone systems. So definition. A matrix A, n by n, is called reducible if there exists a permutation matrix B permutation matrix always has entries in 0, 1, such that, and an integer k between 1 and n minus 1, such that after you apply P transpose to A, you get a matrix like this, and here you have a block of zeros. This is the important case, with 0 denoting a block of zeros of size n minus k by k. So this is the definition. Sorry that this is so long, but this is the definition of when a matrix is reducible. You apply to it, you apply a coordinate transformation for a permutation matrix. P transpose is P minus 1. This is the same thing for permutation matrix. So this means that this is just a coordinate transformation you apply. And after you apply a coordinate transformation, you get a matrix with this structure where in particular you have there a block of zeros. And now I want to explain what this means. It's very easy to understand what this means intuitively. So explanation. And I like to give explanations from dynamical systems theory. So let's consider this. Let's consider this linear system. And I want to explain what this means. And now define a new state vector as Pxt. Now, what is a permutation matrix? What does a permutation matrix do? Permutation matrix just reorders the vector. So it takes the vector x, and when you multiply the permutation matrix, all it does is a reordering of the xi's, so that now they appear in some different order. Maybe like this, maybe like this. It depends on the permutation matrix. But this is just a reordering of the state variables. So this is nothing. This is just giving the state variables a new name. The one that was x1 is now called x3, and the one that was called x2 is now called x1, and the one that was called x3 is now called x2, and so on. But this is really a meaningless transformation. You just relabel your state variables, but in that case, the labeling of our state variables is usually arbitrary, so it doesn't do nothing. Now consider the dynamics of the Z dots. So this is like this, but X dot from here is like this. And because Z is Px, X is P minus 1 Z. This is from this definition. But for a permutation matrix, P minus 1 is just Pt. So I can write here, instead of X, P transpose Z. This is just P transpose Z. So instead of X, I wrote P transpose Z. And now, because the matrix is reducible, I get F, if assuming that the matrix is reducible, I get this. So what does this mean? This means that if I take my Z vector and I separate it into two parts, the upper part includes K coordinates and the second part includes N minus K coordinates. So I got this equation. I just want to explain now what it means. So to explain what it means, I break Z1 into, so instead I take Z and I break it into the first K components, I call it Z1, and the next N minus K coordinates, I call it Z2. I just break it into two vectors. And then I get these dynamics because the matrix is reducible. So what does this dynamic mean? This means that Z2 dot is HZ2, and Z1 dot is FZ1 plus GZ2. So inside my linear system, there is a smaller independent linear system. The Z2 system is smaller. It has dimension n minus k. Since k is between 1 and n minus 1, n minus k is between n minus 1 and how much is this? 1. So it is a smaller linear system. It has dimensions smaller than n, which is completely independent. It doesn't depend on Z1. It only depends on itself. What did I write? Z2 dot is equal to Z2. So you can think of your linear system in these coordinates. It's like this. You have the Z2 dot, which only depends on Z2. And this feeds the Z1 system that depends on Z1 and on Z2. But in some sense, the system can be reduced. First of all, understand the smaller linear system, and then you can understand the entire linear system. So this is FZ1 plus GZ2. So you can reduce the study of your n-dimensional system to the study of a smaller system, smaller independent system, Z2. So this is the meaning of reducibility. Reducibility means that you can take your agents, your zi's, so another interpretation. You take your vector of z's, after you perform the permutation, you take the vector of z's, and you can decompose them into Z1 and Z2. Z2 only talk to one another. The vectors here, the components of Z2, only talk to one another, and they feed Z1, and the Z1s also talk to one another in the dynamics, but there is no arrow from Z1 to Z2. Z2, the vectors in Z2, they talk to each other, and only to each other. Then they compute Z2, and then this information is fed to Z1. So Z1, they talk within the group of Z1 and also get an input from Z2. So in some sense, this corresponds to a graph which is not connected. Why is it not connected? Because you cannot move from here to here. You can move from here to here, maybe you can move inside here, you can move inside here, but there is no arc in this graph that takes you from Z1 to Z2. This is more or less the intuitive interpretation of reducibility. So this is in some sense a degenerate situation because it means that when I want to study somehow A, I can reduce it to studying the smaller matrices. So this is a degenerate case, but it is important. And a matrix is called irreducible matrix. Is called irreducible with an I here if it is not reducible. Sorry. Matrix A is called irreducible if it is not reducible. So this condition never holds. Whatever permutation matrix you take, you can never find a smaller system, independent system, hiding in your large-scale system. Okay, so now we can give a theorem. Questions about reducible and irreducible matrices. Perhaps some of you, I'm sure some of you already don't do this, but I just wanted to give an intuition and also an interpretation in terms of dynamical system theory. Questions about this? No questions. Okay. So now we can do the theorem. The system, okay, consider x not equals fx, a nonlinear dynamical system. If Jx and Jacobian is Metzler and irreducible for all x in the state space, then the system is strongly monotone. So this is the condition that we needed in order to have this strong monotonicity rather than just monotonicity. So again, I just remind you what this means. It means that if you take two initial conditions, one smaller than the other, and of course you assume they are not equal, then after arbitrarily short time, your system will already reach the situation where the solution corresponding to P is strictly smaller than the solution corresponding to Q. So not only it preserves the ordering, okay, if I had here smaller or equal, this would mean it preserves the ordering, but it does a little more than preserving the ordering because the two solutions are strictly separated. Each coordinate here is strictly smaller than each coordinate here. So the condition needed is that the Jacobian is Metzler and irreducible rather than just a Metzler. So before we prove this, we will prove this in a minute because I think the proof gives a little bit of intuition. Before we prove this, let me speak about the RFM. Let me speak about what does this say about the RFM. And then we will prove this tomorrow morning. Tomorrow morning we will start by proving this. Tomorrow morning my time. We will start by proving this, 0 and 10. And then we will proceed to networks of ribosome flow models. So for the RFM, let's take again an RFM of dimension 3. Just for simplicity, everything I say works for any dimension. Or consider the RFM. I want to show you that it is actually strongly monotone, and not just monotone. Up to now, we only said that the RFM is monotone, but actually it is strongly monotone. That's what I want you to know. And this is also true for the RFM R. So we compute the Jacobian. Okay, sorry, no, I can't prove this yet because I didn't give you a condition for irreducibility. No. Then I'm too early. Sorry. Forget about that. We need something before. We need something before that. We need a graph theoretical condition for irreducibility. Yes. So let's go back to our matrix A, and I will just give a nice graph theoretic condition for A to be irreducible. And this is as follows. You take A and you generate a graph with n nodes. You generate a graph with n nodes because A is n by n. Now, every time you see an entry AKL not zero, you look at the entries of A. Every time you see an entry not zero, what you do is you add an edge with k different from L. You're not interested again in the diagonal entries. You don't care about them. You look at entries in your matrix which are off diagonal and non-zero, and then you add a directed edge from K to L, from node K to node L. You go through all the entries, the off-diagonal entries in your matrix, and every time you see an entry which is not zero, you add in your graph an edge from node K to node L. And in this way, you get a graph, I think sometimes it is called the adjacency graph corresponding to A, and A, so this is a theorem, say, A is irreducible if and only there is a path from any node, say I, to any node J in the graph. And I and J are two different nodes. So the A is irreducible. When you look at the graph, you are supposed to see that you can go from any I to any J, and from any J to any I, from any two different nodes, you will always find a path. And the intuition is, again, that if this is irreducible, if A is reducible, then you can divide it. You saw, like, we saw that we had this intuition that when A is reducible, this corresponds in some sense to one-sided communication or asymmetric communication in your graph. And this is exactly what we say here. If there is a path from any node to any node, then this means that you can never transform A using a matrix P to the reducible form, because the reducible form shows that some of the nodes don't talk to one another. So, okay, I think that's enough for today. In the next lecture, I will show you, using this, that the Jacobian of the RFM is always irreducible, and therefore the RFM is a strongly monotone dynamical system. Then we will prove why Metzler plus irreducible implies strong monotonicity. I think the proof is interesting. And then we will speak about networks of RFMs. So, questions, please. We have 1 more minute if you have questions.
Questions from the audience side?
Michael, for proving equilibrium state that is globally stable for RFM, does we need irreducibility as a condition, or we need only cooperativity plus unique equilibrium point?
Yeah, I'm sorry, I couldn't hear you well. Can you speak a little bit slower?
Yeah, maybe I can increase my volume. Wait, am I audible now? Yeah.
Yes, a little bit slower because the
Yeah,
speaker.
sure.
Sure.
So for proving the stability in RFM, we need the condition cooperativity plus unique equilibrium point that we show for the RFM system. So does we need a irreducible matrix, their condition there also?
So we proved stability in the RFM first using contraction theory, and
Yeah.
then reducibility, we didn't matter about this. We just looked at the Jacobian and calculated some negative matrix measure. And then we proved that everything in the RFM converges to an equilibrium using Gian theorem. Gian theorem actually does not require strong monotonicity. That's why I didn't talk about strong monotonicity yet. It only required standard monotonicity, so to speak. So
Yes.
to prove stability in the RFM, we can rely only on the theory of monotone dynamical systems. We don't need strongly monotone.
Yes.
But as we go forward to networks of RFMs, there the results, Gian's theorem is not enough, and we need the results from strongly monotone dynamical systems. So that's why I started explaining this notion now before we move to networks of RFMs.
Yeah, now I'm clear about networks. Yeah.
Thank you, Aditi.
Any
More
other
questions?
So if there are no queries, so let's close this session. See you all tomorrow.
Thank you, Arvi. Thank you very much. See you all tomorrow morning, my time. Bye.